Okay. Yeah, thank you very much for coming to this talk and in particular for inviting me. It's a great pleasure to speak about my work here, which is joint work with Amitabh Basu, Marco Di Somma, and Martin Skutella in one paper, and with Christian Haase and Georg Loho in the other paper. So this talk is about understanding neural networks from a mathematical perspective. But before we come to that, let me maybe share a news headline, which I discovered 2 days ago. So there was a photography competition. And so apparently the winner admitted after winning this competition that the image actually was generated by an AI. So the purpose of this was to boost the discussion how we should deal with AI as a society. And I just would like to share this in order to encourage everyone to join this discussion, because I think thanks to ChatGPT, everyone is discussing this right now, and it's a great thing. So just, yeah, I think it's very important. And yeah, just one thing I wanted to mention before coming to the fun math part of this talk. So if we want to talk about the mathematics of neural networks, then we should first probably define which model we are looking at. And this is the model of ReLU neural networks. So what is a ReLU neuron? A ReLU neuron is just a node in a computational graph. And as inputs, it receives the outputs of previous neurons. It takes a weighted sum with some weights W here, and then it applies an activation function. And in our case, this activation function is the rectified linear unit, and that's why it's called ReLU neuron. So we just take the maximum of this weighted sum and 0. So basically the ReLU unit kills negative components. And that's what it looks like. So if you look at the function computed by one ReLU neuron as a 3D image, so this would be a function from R2 to R, then it looks like this. So first a weighted sum would generate a hyperplane, which looks like this as a graph, and then the ReLU activation function would flatten out the negative part of this hyperplane and set it to 0. So we would obtain one break line here and 2 linear pieces. Okay, so that's a single ReLU neuron. And if you take these neurons and plug them together into one neural network, so into one network, then you obtain a ReLU neural network. And we usually assume that this is acyclic and layered. So though layered is not really a big constraint, but let's just do it for simplicity. Then it looks like this, and this example will compute a function from R2 to R3. And another way of viewing this neural network is it's just a composition of an alternating composition of linear transformations and component-wise applications of this ReLU function. So we would not apply a ReLU at the inputs or outputs, just at these inner neurons. And then the whole function would first be mapping this 2-dimensional input vector to R3 in this example, applying ReLU component-wise, having another linear transformation, having another component-wise ReLU, and having a third linear transformation to obtain our 3-dimensional output here. And now we would say that this ReLU neural network has depth 3 because we have 3 of these linear transformations. Or another way to phrase it would be it has 2 hidden layers. So the hidden layers is just the number of ReLU layers in between. And that's always 1 less than the depth, just by convention. Okay, so by the way, if you have questions during the talk, just interrupt me anytime. I think it's much better to clarify questions straight away. So that would be the first point at which I'm asking you whether you have any questions. If not, then let's move on. So the main question I would like to investigate today is, if we have these ReLU neural networks and we fix a certain depth, what is the class of functions we can represent with such ReLU neural networks? And yeah, so here, the first thing that comes, for many people, the first thing that comes to mind is this universal approximation theorem, which says okay, if I have one hidden layer, then this is already enough to basically approximate any continuous function. You need some assumptions. Usually you assume like the function is defined on a bounded domain. And yeah, so there are different versions of these universal approximation theorems. Yeah, but I say if you really want to understand what's going on in these ReLU neural networks, then you should maybe understand more. So maybe we should even understand what is the exact class of functions we can represent. And yeah, so here things are much less clear, as we will see in this talk. To get started, let's maybe start with a simple, cute example, which is just a maximum of two numbers. So this would be x and y. And to do this as a ReLU neural network, we just subtract y from both sides of the maximum. So this would be x minus y and 0 on the maximum of these two. And then in the end, we have to add y again to make it the same function again. And now the nice thing is that this term is actually a ReLU, so we can implement it as one neuron here, which receives a positive input from x and a negative input from y. And then we would like to pass y directly to the output. Now, as I said earlier, we usually assume these neural networks to be layered. So what we could do instead is to split up y in a positive and a negative part. So if y is positive, then via this path, we would receive y at the output. And via this path, we would receive 0 at the output. And if y is negative, then it would be the other way around. So via this path, we would receive y, and via this path, we would receive 0. Yeah, so that way, a simple neural network with one hidden layer can compute the maximum of two numbers. We can do this, and we can use the same construction to compute a maximum of four numbers by just first doing the same thing for the first two inputs and then the last two inputs in parallel, and then taking again the maximum of the two maxima. Now observe that we don't have activation functions here. So because it's just the output of the first two networks and the input of the second network. And this means that the linear transformation corresponding to these edges combines with the linear transformation of these edges into one big linear transformation from this ReLU layer to this ReLU layer. So in other words, we only have two hidden layers in this example to compute the maximum of four numbers. And we can repeat this just by doing the same thing again. And with each new hidden layer, we would be able to double the number of numbers we take the maximum of. Or to phrase it the other way around, by this construction, we can compute the maximum of n numbers with a logarithmic number of hidden layers. Yeah. Okay, so far so good. This was a nice maximum function, so like maybe a basic starting example. But in fact, it's much more important, as we will see. It's not just a simple example. And for that, let's ask the question, what is the general class of functions we can represent by ReLU neural networks? And the first observation is, if you have a ReLU neural network, then all its components are just like linear transformations and the ReLU function, and both of them are continuous and piecewise linear. So if you plug them together, then the composition of them must be continuous and piecewise linear as well. So with CPWL, I exactly mean the class of continuous and piecewise linear functions, and I will use this abbreviation a lot. Okay, now we have this nice observation, and the big question is the converse true as well? So if a function is continuous and piecewise linear, can be also represented by a ReLU neural network. And for that, there's this nice theorem by Wang and Sun from 2005. And it says, if you have a general continuous piecewise linear function f, which is defined on Rn, so n is the input dimension, then we can write it as a linear combination of maxima of n plus 1 linear terms. And now the important thing is that it's exactly n plus, or at most n plus 1 linear terms here. So we might have many of these maxima terms. I'm not saying what P is in this theorem, but it's some finite number. And the important thing is that each of these maxima terms contains at most n+1 linear terms. Okay. But the nice thing about this theorem is now representing an arbitrary piecewise linear function boils down to representing a bunch of maxima terms. So from this, we can easily obtain that a general piecewise linear function f, continuous piecewise linear function, defined on Rn, can be represented by a neural network by just using this representation and representing the linear terms here, the maxima, and taking the linear combination as a final output. So since all these maxima terms can be computed in parallel, the amount of layers we need is logarithmic in the input dimension n. And I'm not talking about the width. So since this P might be huge, this might be a very big neural network, but the important thing is it's not deeper than logarithm n, basically. Okay, so this is known, this is there. Are there any questions at this point? Yes.
Yeah, I'll ask a stupid question just to get the ball rolling.
Sure.
So you showed that the maximum of n numbers can be represented by log 2n layers.
Mm-hmm.
Is that, can you possibly represent it with fewer layers, or something cleverer than just taking the max pairwise each time?
I mean, that's not a stupid question. It's exactly the question I'm going to ask, not only for the maximum function, but for general piecewise linear functions. So
okay,
hold
so
on.
you will answer that, but yes, okay.
I mean, yeah. You should wait until the end of the talk, and then you can judge yourself whether I answered the question or not.
Okay, I'll get back to you.
Yeah. Okay, so yes, the natural question is, we now know that a logarithmic number of layers is sufficient, but is it also necessary in some cases? And that's a big question here. And my conjecture is, I just pose this conjecture now as it's here. So my conjecture is, yeah, there are functions for which we do need a logarithmic number of hidden layers. So this would be a sharp contrast to the approximation case where one hidden layer is always sufficient. And a nice thing is, if such a function exists, we even know what it looks like. And it's simply the maximum function. So using this representation theorem, which I had on the earlier slide, saying that every function can be written as a linear combination of maxima functions, it turns out that this is actually the most difficult function for a neural network to represent. So figuring out how many layers do we need in a worst case is equivalent to figuring out how many layers do we need to represent this function. So everything boils down to the maximum function, and that's why the maximum function is not just an arbitrary example. Okay, so far so good. Now, if it's just about a maximum function, then yeah, let's just analyze it. How difficult can it be to figure out how many layers you need in order to represent the maximum function? By the way, the fact that here it's a 0 here is without loss of generality. So you can just think of this as being the maximum of 2 to the k plus 1 numbers. And we wonder whether we can represent it with k hidden layers. Okay, so what do we know about this question? The first thing we know is one hidden layer is not sufficient to compute the maximum of 3 numbers. So basically, we do understand pretty well what are the functions representable by one hidden layer. And there are many proofs of this statement. I will just give a very visual one here for you now. So if you look at the function, maximum of 0, x1 and x2, then it's piecewise linear with 3 regions. It has this region where the maximum is 0, it has this region where the maximum was x1, and it has this region where the maximum was x2. And this is the origin. So in particular, the set of breakpoints, so the points where the function is not linear locally, it's the union of these 3 rays. And now let's look at a function represented by a one hidden layer neural network. Or to get things rolling, let's look at a function represented with one hidden neuron. So that's similar to what I showed you in the very beginning. Maybe you remember this 3D plot. So you have a linear transformation, and then you just flatten out the negative part. So you obtain basically one break line. So this would be this one here. So it would be a function which has two linear pieces and one hyperplane or one line in 2 dimensions along which it is not linear. Okay, if you have a second neuron, then the function would be just some weighted sum of these two functions. So you would obtain a second line along which you are not linear. And with third neuron, you might obtain a third line. Now what can happen is that maybe the fourth neuron produces a hyperplane which is already there, and it produces it with opposite signs. So you might cancel that hyperplane which is there already. And then after adding the fourth neuron, the set of breakpoints would be 2 hyperplanes again only, and not 4 or 3. But the important observation is if it cancels a line at some point, then it cancels it everywhere, because like these breakpoints, so the function behaves the same at every point along these breakpoints. So it cannot cancel a line partially or something like that. So if you have a fifth neuron, then you might add another hyperplane as breakpoints, another line. But the important observation is, at the end, no matter how many neurons you add here, the set of breakpoints will always be a union of lines. But this union of the 3 rays is not a union of lines, so we cannot represent this function with only one hidden layer. Okay. So this we know. This is there. What else do we know in terms of lower bounds and the depth? And it turns out nothing. So it's really the only lower bound we have. So in particular, if you want to know, if there's any function which provably needs more than 2 hidden layers, then the answer is we don't know if such a function exists. So in terms of lower bounds, there's a gap between 2 and logarithm of n, basically. And as I showed on the last slide, the smallest candidate for which we don't know how many layers we need is just this maximum of 5 numbers. So 0, x1, x2, x3, and x4. So yeah, the big question is, are 2 or 3 layers the minimum number of layers required to represent this function? Okay, any questions at this point? If not, then let me show you the 2 results I'm going to talk about. The first one is actually 2 hidden layers are not sufficient to represent this function. However, I have to restrict the statement a bit. So we need an additional assumption on the network, which seems plausible, but we cannot prove it at this point. So we would think that every neural network computing this function would naturally satisfy this assumption, or at least it can be easily transformed into one. But this is a statement which we cannot prove. So I will show you the assumption, and then you can judge yourself whether you think that this might be true or not. But under this assumption, we can definitely prove that 2 hidden layers are not sufficient to represent this function. Okay, and then the second result is not only for the special case of maximum of 5 numbers, but even for general n, we prove a logarithmic lower bound. So we resolve the conjecture. However, again, under an additional assumption, this time the assumption is very easy to state. It's just being all weights of the neural network being integers. So maybe you remember the construction for the maximum. There we only used 1s and -1s as weights, and maybe some zeros if you count the arcs which were not present. But in particular, everything was integer. So the takeaway from this result is, if you can do it with less than logarithmically many layers, then you need some weird fractional weights, and you don't know why you should need fractional weights, but we can also not prove that they are not necessary. So yeah, that's the result we have here. Okay, so if there are no further questions, then I would suggest just hopping into this first result and talking about the assumption. Yeah, so here's the assumption. Don't be scared, it's not as complicated as it might look at the first sight. So let's assume we have a 2 hidden layer neural network, which computes this function. And now I claim, so the assumption states that if you have such a neural network, then the only interesting things should happen at places where the relative ordering of the 5 numbers changes. So in other words, if you look at all the breakpoints this neural network might have, and even every neuron of the neural network might have, so if you look at the function computed by that neuron, then all these breakpoints should only be at places where 2 of the 5 numbers are equal, so where the relative ordering of the 5 numbers changes. Okay, so this might be a bit difficult to grasp, but to visualize this, let's maybe go back to 2 dimensions. So our nice example, maximum of 0, x1, and x2. And here, we basically have 3 lines, 3 hyperplanes, along which the relative ordering of the 3 numbers changes. So it's basically just where 2 of the 3 numbers are equal. And it's these 3 hyperplanes. And now the assumption would be that every neuron in the neural network computes a function which is linear within each of these regions. So all breakpoints are contained in the union of these 3 hyperplanes. And that's the assumption. Okay, if you transfer this to 4 dimensions, then instead of 3 lines, we obtain 10 hyperplanes, 5 over 2. Each hyperplane corresponds to 2 of the 5 numbers being equal. And these 10 hyperplanes divide the input space into 5 factorial 120 regions, because each region corresponds to 1 permutation of the 5 input numbers. And it turns out that each of these regions is what's called a simplicial cone. So it basically looks like this, but just in higher dimensions. So it is a cone which has the 0 as its apex, and it's spanned by 4 extreme rays in 4 dimensions. So in 2 dimensions, each cone is spanned by 2 rays, as you can see in this picture. And in 4 dimensions, each of these cones would be spanned by 4 extreme rays. Yes. So, and the assumption would be that within each of these cones, the function computed by each neuron in the neural network is in fact linear. If you count the total number of extreme rays occurring that way, then it's 30. So this you can just do by some discrete combinatorial geometry. And so why is it not like 120 times 4? Because each of these extreme rays is reused a lot of times. So that's why it's only 30 in total. Okay. And now here comes the nice observation, which makes this case tractable. The observation is, if you look at the vector space of all continuous and piecewise linear functions satisfying this assumption, then this vector space is only 30 dimensional. So why is that? The reason is, once you fix the function values on each of the 30 extreme rays, the function is completely determined. And it turns out that you can also independently fix all these 30 rays, so it's really 30 dimensional and not less. Yeah. And this makes our very complicated problem talking about the space of all continuous piecewise linear function. It boils it down to a finite dimensional problem. And with finite dimensions, we can deal. First, let's do some observations. So if you, as I said earlier, we understand quite well which functions can be represented by one hidden layer, and you will figure out that this is a 14-dimensional subspace of the 30-dimensional space of functions satisfying our assumption. Now, after two hidden layers, we don't understand that well which functions we can generate, but at least we can generate some and see whether they are linear independent and what kind of subspace they span. And it's not too difficult to generate 29. So 29 linear independent functions. So it turns out that after two hidden layers, just by this constructing some functions, we obtain a 29-dimensional subspace of the 30-dimensional space, which can be generated by two hidden layers. And the big question now is can we also represent the 30th dimension, or can we not represent it? And it turns out that this function we are interested in is, of course, not contained in the 29-dimensional subspace. So asking whether this can be represented by two hidden layers is equivalent to asking whether this space representable by two hidden layers is actually 29-dimensional or 30-dimensional. Okay. And yeah, what I haven't told you yet, we do this by a computational proof, so computer aided. What we do is we use mixed integer linear programming. So how exactly does this work? This program will model the function computed by one neuron in a second hidden layer, and it will ask whether this function is contained in a 29-dimensional subspace or not. So to construct this mixed integer linear program, we need something like 44 continuous variables and 30 binary variables and a few hundred constraints. So it's not too big. And as an objective vector, we choose something which basically is orthogonal to this 29-dimensional subspace, pointing into the 30th dimension. And now the question is, if we solve this mixed integer linear program and we maximize into, like, out of this 29-dimensional subspace, can we obtain a non-zero objective value? And we put this into an exact arithmetics mixed integer linear programming solver, and it outputs 0. So from this, we can conclude that it's not possible to leave the 29-dimensional subspace with two hidden layers. So it follows that a neural network satisfying our assumption on the breakpoints needs at least 3 hidden layers to compute this maximum of 5 numbers. So 2 hidden layers are not sufficient. Okay. So are there any questions on this part?
So is the obstacle to doing this with 6 variables just the programming part of the argument?
Good question. So first of all, 6 arguments is not interesting, because if we cannot represent 5 with 2 hidden layers, then we can also not represent 6 with 2 hidden layers, and 3 hidden layers are clearly sufficient to represent 6. So the next interesting thing would be 9.
Okay.
And yes, if it's 9, then it becomes computationally intractable. So this mixed integer program doesn't work for. I mean, you can start it, you can program it, you can feed it in your computer, but even if you take like Gurobi instead of a exact arithmetic solver, it will not terminate in any reasonable time.
Thank you very much.
Yeah, so Gurobi is like state-of-the-art industry solver for mixed integer linear programs. So even with that, no chance. Yeah. Good question. Thank you. Any other question? I mean, of course, it would be nice to somehow get rid of this mixed integer programming part and find a manual argument for this. Still using the assumption. I mean, even better, not using the assumption. But so far, we haven't found one. Okay. So going from 2 hidden layers to arbitrary depth, we somehow need different techniques. This makes integer programming technique cannot work for like just the general case. And here we have a result which is actually valid in general. So no matter how many input numbers you have, we can prove that logarithmic depth is necessary if the weights in our neural network are restricted to be integers. So how do we prove this? For this, we use polytopes. So why polytopes? Here's some kind of motivation which you might be familiar with. If you don't know the words on this slide, don't worry. If you do know, then yeah, that's nice. But I will explain everything you need on the next slide. But for now, let's observe that a continuous piecewise linear function can be written as a difference of 2 convex continuous piecewise linear functions. So the first function might be some arbitrary function, but you can represent it as a difference of 2 convex functions. Okay. If you have 2 convex continuous piecewise linear functions, then this is basically what people in tropical geometry call a tropical polynomial. And a difference of 2 tropical polynomials in tropical world would be a tropical rational function, because difference is tropical division. So dividing 2 polynomials is nothing else than having a rational function. So yeah. Basically, this means that every continuous piecewise linear function can be represented with 2 tropical polynomials, which are like tropically divided by each other. Okay. And that's where polytopes come into play, because for tropical polynomials, you can associate an object called Newton polytopes with them. And the idea of what's coming now is to study these Newton polytopes. But actually, you don't need to know any tropical geometry. It's just like a point of view, I would say. And I'm going to explain what's going to come now just in terms of polyhedral geometry. So what is the Newton polytope of a convex continuous piecewise linear function? So if you have a convex piecewise linear function, then you can write it. So just imagine the graph of this function, which has some facets, and you can represent this function just as the maximum of all the linear pieces which occur in the graph of the function. So it can be written that way. It's just a maximum of a bunch of affine terms, or linear terms in this case. And then the Newton polytope is simply defined as the convex hull of the coefficient vectors of this function. So that's a convex hull of finitely many points, so it's a polytope. And the nice thing is that it somehow relates to the geometry of the original function in some dual way as follows. So look at this example. You have the maxima of 0, x1, and x2. And then the Newton polytope would be the convex hull of the origin for 0, the first unit vector for x1, and the second unit vector for x2. And the graph of the function has 3 pieces, and a set of breakpoints would be these black half-rays here. So then the Newton polytope has 1 vertex for each region of the original function, and has 1 edge for each pair of regions which are adjacent to each other. So in that sense, it is dual to what I call here the underlying polyhedral complex of the continuous piecewise linear function. Okay. So this is Newton polytopes, just a nice little definition. And now the powerful thing is that these Newton polytopes are kind of isomorphic to the set of convex continuous piecewise linear functions with respect to a couple of nice operations. So first of all, if you multiply a convex CPWL function with a positive scalar, then that's the same as scaling the Newton polytope by the same positive scalar. And second, if you add 2 of these functions then what you obtain is another convex piecewise linear function whose Newton polytope is the Minkowski sum of the original two Newton polytopes. So the Minkowski sum is just the set of points which can be written as a sum of points of the two original polytopes. And finally, if you take the maximum of two convex piecewise linear functions, then what you basically do is you just take the union of these linear terms here and take the maximum off. So in the terms of Newton polytopes, you just take the union of all these coefficient vectors and take the convex hull of them. So the convex hull, no, so the Newton polytope of the maximum of two convex continuous piecewise linear functions is just the convex hull of the union of the two Newton polyhedral. Okay, so far so good. Are there questions on this? If not, then let's look at the consequences on neural networks. So what we are going to do is to go through our neural network layer by layer, as you see in this like two hidden layer example on this slide. We look at the Newton polytopes which can occur from the continuous piecewise linear functions represented by the neural network. So at the very beginning, we just have single points. Why points? Because what we compute before we even have a ReLU activation function is always linear. So the Newton polytope is just a convex hull of one point, and that's a point. And this is still true even after we did the first linear transformation, because it's still a linear function. And now the first interesting thing happens. We take the first ReLU activation function, which means we take the maximum of 0 and some linear term. It's a maximum of two things. So the corresponding Newton polytope will be the convex hull of 2 points, and that's a line segment. And now it gets more complicated. So you get another affine transformation, and an affine transformation by this next layer here, and an affine transformation corresponds to taking a Minkowski sum of a bunch of things. So the Newton polytopes which occur here are what's called zonotopes. And zonotopes by definition are just Minkowski sums of line segments. It's a special class of polytopes which is well studied and well understood. Okay, so after applying the next ReLU layer, things become a bit more nasty. So the Newton polytopes here, the ReLU will be like taking a convex hull of a union of two polytopes again. So this class P2 prime will just be the polytopes which can arise in that way from two zonotopes. And then you have a final affine transformation in this example, and this would correspond to another finite Minkowski sums of polytopes in this class P2 prime, and this gives us the class P2. Okay, so that way we can represent, we can give a recursive definition of the polytopes which can arise as Newton polytopes from a neural network with two hidden layers. So if we are interested in whether we can represent the maximum of 5 numbers with such a neural network, then we have to look at the Newton polytope of this function. And similar to the triangle I showed before for the maximum of 3 numbers, this would be a simplex in 4 dimensions with 5 vertices. So it's just the convex hull of 0 and the 4 unit vectors in 4-dimensional space. That's this simplex, which I call delta 4. Now, it would be natural to ask whether delta 4 is contained in P2, but that's actually not the right question to ask, as it turns out, because intermediate functions computed by this neural network might be non-convex. So in the end, you have to look at the difference of 2 functions. If you look at the difference of 2 functions in terms of polytopes, this corresponds to such an expression. So the actual question we need to ask to answer whether we can represent this function with 2 hidden layers is, are there 2 polytopes Q and R in P2 such that Q plus delta 4 equals R. Yeah, so this is, yeah, due to the fact that intermediate functions might be non-convex. Okay. Any questions on this at this point? If not, then let's generalize this to more layers. That just works in a straightforward way. So you start with the class of points. P1 would be the class of zonotopes. And then Pk arises as the class of polytopes, which arise from Pk minus 1 by taking the convex hull of the union of two of these polytopes and taking a finite Minkowski sum over these polytopes. And similar to the 4-dimensional simplex, we can define the n-dimensional simplex as the convex hull of 0 and the first n unit vectors. And then to rephrase our conjecture about neural network expressivity in terms of polytopes, we ask whether there are polytopes P and Q in Pk such that P plus the 2 to the k dimensional simplex equals Q. And this conjecture is equivalent to asking whether the maximum of 2 to the k plus 1 numbers can be represented with k hidden layers. So we translated our conjecture into purely polyhedral terms. They are just polytopes, Minkowski sums, and convex hulls, and nothing else anymore. Okay. We have this conjecture. I told you we are able to prove our original conjecture for integer weights. And this we do by proving that this polyhedral conjecture is true for lattice polytopes. So lattice polytopes are polytopes where all the vertices have only integer coordinates. And since if you look at the Newton polytopes of functions computed by integral neural networks, these polytopes are lattice polytopes. We then obtain that for integral neural networks, we cannot compute a maximum of 2 to the k plus 1 numbers with k hidden layers. So I will give you a very brief overview of how we show this. The first step is to translate it into this polyhedral world, of course. And then the second step would be to, again, look at these polytopes layer by layer and subdivide them into easier polytopes. So if you have a Minkowski sum of this blue polytope and the red polytope, there's some way you can subdivide it such that the red polytope and the blue polytope are in the subdivision, plus some other polytopes, which are basically Minkowski sums of faces of these two polytopes. And okay, it doesn't matter why and how exactly we do this. The only thing I want to give you as a takeaway is that this allows us to transform complicated polytopes into subdivisions which contain easier polytopes, which we somehow do understand. And then, as a third step, what we do is we look at the volume of these polytopes, but not at the actual Euclidean volume. We somehow normalize it by, yeah, this normalization depends on the affine hull of the polytope and the integer points how they arrange in this affine hull. So it's not, I mean, it's a standard definition in the theory of lattice polytopes, but if you see it for the first time, it's a bit confusing maybe. But it's some version of the volume of the polytope. And the important thing is that it's always integer if you look at lattice polytopes. And we argue with the parity of these normalized volumes. So basically, the argument in the end is what we can produce with k hidden layers is always something that has even normalized volume. But in order to represent the simplex, we would need something that has odd normalized volume. And that's what everything boils down to in the end. Yeah. And yeah, so by that, we prove this conjecture for lattice polytopes, and therefore we prove our original conjecture for integral neural networks. So in other words, if you want to compute the maximum of 2 to the k plus 1 numbers, then you need at least k plus 1 hidden layers if you want to use only integral weights. Okay. Any questions on this? Hey, if not, then let me tell you what could be next at this point. First, I think that, of course, the next thing is finally prove or disprove the general conjecture for like non-integer weights, for no assumption on the breakpoints. Yeah. And what I think the right thing to do is indeed looking at these polytopes and also looking at these subdivisions. But the volume argument clearly cannot work if you have non-integer weights, because if you allow any fractional weights, then you can just scale your volumes arbitrarily, and it doesn't make sense to look at any parity there anymore, something like that. So I think that these subdivisions might be very helpful also for the general case, but we need a different argument to separate these different classes of polytopes from each other. So the volume cannot be the thing we do here. Yeah. So here's again our translation of the original conjecture into the world of polyhedra. So we have these classes pk, which arise by looking at the Newton polytopes, which can be generated with a neural network by k hidden layers. And we ask whether there are polytopes p and q in this class such that p plus the 2 to the k dimensional simplex equals q. Okay. And with that, I would like to thank you for your attention and for your interest and listening to this talk, and I'm curious which further questions you might have.